Mr. Abbott here, in time for another boring activity explanation. This is the heating and cooling of land and water lab that we did. This is the data that we collected in class using the Vernier probes. Now I plugged it into the computer and graphed it to show you what your graph should look like, but obviously you're going to have to draw your data for 2018, 2019. I believe this was lab number 26. So let's take a look at some of the terms that you should know, beginning with the definitions. Okay, you should have understood, or you should have learned, the idea of specific heat last year. Specific heat is a value. You can find it on the front of the Earth Science Reference Table, but it tells you the amount of energy that's needed to raise 1 gram of a substance by 1 degree Celsius. So when you look on the reference table, any material with a high specific heat like liquid water takes more time to heat up. In this lab, we're heating water with a specific heat of 4.18 degrees, 4.18 joules per gram degree Celsius, and then we're heating soil, which is more like the basalt or the granite, which has a much lower specific heat. Now, the second vocabulary definition you had was radiative balance. For this experiment, we didn't reach a radiative balance. When you look at the angles of insulation activity, we definitely hit a radiative balance. But a radiative balance is a dynamic equilibrium. It's when an object is absorbing and re-radiating the exact same amount of energy. So if something takes in and releases the same amount of heat or the same amount of radiation, the temperature remains constant. Finally, there will be a map where they're going to show you what's referred to as the heat equator. It is an isoline that connects points of the maximum surface temperature. They'll use this sometimes on the regions. Here's an example of a regions question with the heat equator for July and January. You'll see the heat equator varies with the seasons. It also varies whether you're heating water or land, since water and land have different specific heats. So when you look for a definition for it, it's an isoline that connects points of maximum surface temperature. It definitely varies within the seasons. Now, you've got a rate of change calculation to do. So I hope you taped in our data over the data that was on the lab. And here you're asked to do 2 different calculations for the rate of change, one for the soil and one for the water. I am not going to plug all the values into for you. You're looking for the first 10 minutes when the lamp was on. So for the soil ended at a much higher temperature, 49.9 degrees Celsius. The water only reached 30.9 degrees Celsius. So please make sure that you finish these calculations. After you've finished the calculations, please round them to the nearest tenth. All right. So the graph that you have to do, okay, time in minutes is your horizontal variable because it's the independent variable. I would suggest when you do this scale, you start at 0. There's 21 boxes, so each line is equal to 1. I wouldn't write down every number, but if you need to, please go for it. Now, if you look at the vertical axis, right, your temperatures go up to slightly below 50. Okay, the lowest temperature is above 25. So to make this graph much easier, I would begin vertically at 25, and I would be going up by ones. But I wouldn't mark down every single number unless you have to. So that's how I would set up your scales. When you are done graphing this, your graph should look something like this. All right, it tells you at the top to label it or do it in different colors. I am going to do both of these. I will do the water. I guess I should do the water in blue. So the water, the temperatures went up, and then, you know, this is what we observed. The temperatures sort of stayed relatively constant. So that one was the line for the water. I'll use the green, and the green is representing the values that we measured for the soil. You can look at the slope of the lines and see there is a significant difference in the rate at which the water and the soil heated up. Now let's take a look at the questions that you had on the back. Well, actually, there were a couple of questions on the front that we should look at before we look at the questions on the back. Okay, from the front, okay, the questions, there's the diagram. Okay, you've got two different containers heated with a lamp. We happen to use a 300-watt lamp, which was a really strong lamp. One thing that you should notice about these is they're definitely the same distance away from each other. You also should understand that you have the same mass. Okay, you've got the same amount of water and soil that are being heated from the same distance. It's important to set them up so they're the same distance, so that both of the containers receive the same amount of energy. Clearly, when you looked at your graph, the soil heated much more rapidly, but it also cooled much more rapidly. Okay, materials with a low specific heat heat rapidly and cool rapidly. So if we flip to the back of this, when you're looking at the back of the lab, you have questions 4 and on. Okay, which is a better absorber and radiator of the heat energy? Clearly, the soil heated and cooled more rapidly. Which material has a higher specific heat? That one you should be able to figure out. You can look it up on the reference table. For the soil, I would use either the granite or the basalt as your model for basic sort of rock material. 3 p.m. on a summer day, we've all been to the beach. Okay, you know the sand heats up more rapidly, so the sand is heating the air above it. So over the water, it should be cooler, and over the nearby land, it should definitely be warmer. So the air over the ocean tends to be cooler than over the land in the middle of the afternoon. We'll see that that sets up conditions known as land breezes and sea breezes when we get to our weather unit, which comes after energy. Now, for number 7, you need to figure this out yourself. You should remember the relationship between temperature and density. You need to think about the molecules of the material. Okay, when you heat a substance, the molecules spread out. Okay, so you should know that as temperature increases for most materials except ice, as temperature increases, density is going to change. The molecules spread apart, so they should become less dense. So think about the density and temperature relationship to answer this question appropriately. Now, here is your map of the heat equator. One thing that you need to be careful of is the equator. The actual equator is right here in the middle. And looking at that, they've got a big distortion in terms of the northern hemisphere and the southern hemisphere. One thing you definitely want to notice that in the southern hemisphere, there's a lot less land mass. Okay, in the northern hemisphere at this point in geologic time, there's a lot more land in the northern hemisphere and the southern hemisphere, and that definitely has an impact on the rate of heating, because we know that water heats slowly and cools slowly. At least that's what we saw in the data we collected. So for question 8, also I'm not giving you an answer, but I'll give you a suggestion of what you should be thinking about. Why does the heat equator of January bend farther into the southern hemisphere over the continents than over the oceans? Well, they're really asking you to compare the rate of heating for water versus land. Okay, so what do you know about the rates of heating for water and land that can explain a larger change over the continental areas? The last question you need to consider, and I've already sort of given you an idea, for question 9, why does it move farther in the northern hemisphere in July than in the southern hemisphere in January? Okay, thinking about the distribution of land masses, that would help you to come up with an appropriate response for this question. So in summary, I can give you an idea. Here's another Regents question that sort of shows you the type of setup. The idea is that land and water heat at different rates because they're different materials. The specific heat determines how rapidly something heats up. So when you're comparing water to soil, the water is going to have a high specific heat. And because it has a high specific heat, it heats and cools slowly. It takes more energy for water to heat up, but more energy for water to cool down. When you look at soil, soil tends to have a low specific heat. Materials with a low specific heat are going to heat and cool rapidly. This really means that our climate here on Long Island gets moderated or changed by the fact that we're surrounded by the ocean and Long Island Sound. I hope this helps, and I hope that you are enjoying your Lab Fest. Take care.